Converting and running digital Multisim live circuits in TINACloud. In this video we will demonstrate how to convert and run digital circuits from Multisim Live using TINACloud. This feature of TINACloud and Tina is especially valuable since Multisim Live does not currently support conversion of digital circuits into MS14 format, limiting their use in the offline Multisim environment, while Tina ensures seamless conversion of any MSJS format files and simulation of the converted circuits in both TINACloud and the offline Tina environment. We will use a half adder circuit for this example, which we have already downloaded to our hard drive. To begin, open the file in TINACloud using the upload command. Testing the digital circuit. Once the circuit appears in TINACloud, we can begin testing. A great feature of TINACloud is its ability to display digital states, not just on the output, but on any visible digital node on the screen. To start the interactive digital simulation, press the Dig Interactive Digital button. Let's change switch A to high. You will see the state change at the sum output. Next, if we set the other input switch to high, it again appears at the sum. However, if both the A and B switches are on, both inputs are high, the sum becomes low and the carry becomes high. This confirms the standard operation of a half adder. VHDL and Verilog subcircuits. TINACloud and Tina also offer another powerful feature. Digital circuits can be described using mathematical formulas or programming languages. In particular, digital circuits can be modeled and simulated using hardware description languages, or HDLs, such as VHDL and Verilog. The importance of VHDL and Verilog lies in the fact that these descriptions can be synthesized into integrated circuits, such as FPGAs, which are a standard solution in modern electronics. To demonstrate this method, let's add two subcircuits into TINACloud, the half-adder VHDL and half-adder Verilog macros. The upper circuit shows the description of a half-adder using VHDL syntax. This code is placed within the macro. To view the code, simply double-click the macro. Then in the Properties window, click the three dots, Details, at the end of the HDL line. The HDL code window will appear. Similarly, you can view the Verilog equations within the Verilog macro by following the same steps. Double-click the macro and click the three dots in the HDL line. Now, let's close these windows and compare the results in TINACloud's interactive digital mode. Comparing results. Now press the interactive digital button again. If only one input on the original gates is high, the sum is high. You can see that the VHDL and Verilog macros produce the exact same result. Now, let's test the case where both inputs are high. In the original circuit, the sum is 0 and the carry is high. The VHDL and Verilog representations match this perfectly. Why use HDL? Today, it is very common to describe digital circuits using HDL code instead of building them from individual logic gates. Hardware description languages such as VHDL and Verilog allow designers to work at a higher level of abstraction, making development faster and more efficient. While this example is simple, the same approach is used for designing much more complex digital systems. For more information on creating and uploading digital circuits to Xilinx and Intel FPGA boards using VHDL, Verilog, or schematic designs, visit our YouTube channel, www.youtube.com, @Tina Design Suite. Analyzing a 4-bit digital counter. Introduction and circuit import. Our next example is a 4-bit digital counter composed of 4 JK flip-flops. To begin, we'll convert the Multisim circuit into TINACloud using the standard import process. Once uploaded, the schematic will appear directly on your TINACloud workspace. Interactive simulation. We can analyze this circuit either interactively or through a timing diagram. Let's start with the interactive digital mode by clicking the Dig button. As the simulation runs, you can observe the signal propagating through each flip-flop until it reaches the final PR4 output. While this provides a real-time look at the logic levels, following the high-speed operation manually can be challenging. Digital analysis and timing diagrams. To get a clearer picture, it is better to generate a timing diagram. Navigate to the analysis menu and select Digital. In the pop-up window, set the analysis time to 20 milliseconds. Click Run to generate the waveforms. Frequency division results. The resulting waveforms clearly demonstrate the frequency division at each stage. PR5 input clock. This is the high-frequency digital input signal that serves as the base for the counter. PR1, first stage. The frequency at this output is exactly half of the input signal. You can see 2 clock cycles in PR5 for every 1 cycle in PR1. PR2, second stage. The signal continues to divide, resulting in a frequency that is 1/4 of the original input. PR3, third stage. This waveform is 8 times slower, 1/8 frequency, than the input PR5. PR4, final stage. At this final output, the frequency is 1/16 of the input signal frequency. The diagram confirms the binary counting behavior. Each successive flip-flop stage triggers at half the previous stage's cycle, effectively doubling the period and halving the frequency at every step. This feature makes the circuit applicable as a counter. Each output represents a bit in the digital counting result. The output with half the input frequency corresponds to the least significant bit, LSB, while the output with 1/16 of the input frequency corresponds to the most significant bit, MSB. Let's add a hex display to the circuit to demonstrate this. Press the dig button. The counting result appears in hexadecimal form on the display from 0 to F, and then restarts. '74LS193 Integrated Circuit Demo. Our final example features a digital integrated circuit, the 74LS193 synchronous 4-bit binary counter. Just as before, we can convert this circuit from Multisim Live into TINACloud and run it interactively. This specific circuit is configured to count down from hex F to 0 and then reset. Let's see it in action. Interactive simulation. Press the dig button to start the simulation. As you can see, the circuit is counting down, and once it reaches 0, it will automatically start the cycle again. Compatibility and expansion. It is important to note that you can convert all digital integrated circuits from Multisim Live. Furthermore, TINACloud supports all digital ICs from the Multisim offline environment, as these components are also native to the TINA library. Conclusion. That brings us to the end of this tutorial on converting digital Multisim Live circuits for use in TINACloud. Beyond standard logic, TINA and TINACloud support more than 1,400 microcontrollers, including PIC, AVR and Arduino, 851, HCS and STM, ARM, TI Tiva and TI Citara, Infineon XMC and ESP32. Be sure to check out our other videos on converting microcontroller circuits from the offline version of Multisim into TINA and TINACloud, as well as our additional microcontroller circuit examples for these MCUs in TINA and TINACloud. Thank you for watching. For more information, visit us at www.tina.com or find us on YouTube, www.youtube.com@TINA Design Suite.